Hello and welcome everyone to Red Planet Live. I am your host, Ashton Zeth. I'm elated to be hosting the Mars Society's podcast and leading the conversation about human exploration of the universe and the future settlement of Mars. As a longtime space enthusiast, I am passionate about STEM education and making humanity an interplanetary species. Thank you everybody for joining today and supporting Red Planet Live. Going to kick off today's episode with just a couple of reminders. You've heard me say them before. If you haven't heard, the 2025 International Mars Society Convention is scheduled for October 9th to the 11th. That's a Thursday to Saturday at the University of Southern California in Los Angeles. This year, we're celebrating the 28th year, and the theme is Mars, the Time Has Come, and we'll focus on Mars exploration, human settlement planning, and cutting-edge technologies. So if you're interested in sharing your insights at the conference, you can submit an abstract of 150 to 300 words via our Mars Society abstract page. The deadline for that is Friday, June 27th at 5 p.m. Mountain Time for consideration. So if you've got some insights, if you've got a story to tell, if you've been doing some research and you want to share that with the attendees of the conference, click on that link right there and then you could submit your abstract. I want to remind everybody as well that the Mars Society has launched our capital campaign to upgrade the Mars Desert Research Station, also known as MDRS. And this is a vital habitat where scientists, engineers, and students will simulate life on Mars right here on Earth. Your donation directly supports critical improvements to this one-of-a-kind research facility, and every donation does include a special perk as a thank you for being a part of the mission. So head to that link right there that you see to donate and contribute to the Mars Desert Research Station. All right, we're going to jump right in. I'm excited, on brand, talking about Mars, the upcoming convention. I'm excited to be speaking with today's guest, who is Dr. Katie Stack Morgan, who is a planetary geologist at NASA's Jet Propulsion Laboratory, JPL, where she serves as the acting project scientist for the Mars Perseverance rover. She plays a key role in mapping Jezero Crater, ancient river delta, and guiding the rover's collection of rocks and soil samples, which are obviously, as we know, critical towards the first ever Mars sample return. Katie earned her BA in Astronomy and Geosciences from Williams College and completed her PhD in Geology at Caltech. She has contributed extensively to both the Curiosity and Perseverance missions, advancing our understanding of Mars' watery past and the potential for supported life. Katie, thank you so much for being here.
Thank you, Ashton. It's great to be here with you today.
I'm excited to be chatting with you. I mean, obviously, this is Red Planet Live. We talk about Mars, so this is so on brand for us to be talking about your background and your work with the Perseverance rover. So excited to learn more. Going to kick off today's episode the way that we always do with question of the day. It's just a segment meant to be an icebreaker. I promise, no right or wrong answers, but just curious what your thoughts are. So today's question of the day, I was thinking about a trip to Mars and what would humans do to entertain themselves, keep themselves busy on that long journey, and then what do they do when they get there? So the question is, what is your favorite board game that you would take on a trip to Mars?
Okay. Ooh, this is a good question. Well, okay, I'll just say the first thing that came to mind, which I don't know, for any 90s kids out there, there was a game called Uno Rummy Up.
Okay. Yes.
And it's like Uno, but with tiles. Although now that I'm thinking about it, a game with a lot of small tiles is probably not the one you want to put on a spacecraft to Mars in case you lose one. But it's the one that came to mind because it is endlessly fascinating, interesting combinations. And it's like Uno, but on a game board, kind of with little tiles that are the Uno cards. So that's the first one that came to mind because it's fun. It engages the brain. But again, now that I'm thinking more about it, we're going to lose those tiles somewhere in the spacecraft. So I might have to think of another one later.
No, that's a good answer. I mean, as another 90s child, I do remember Uno. I don't remember specifically that one.
It's a niche game. I don't know a lot of other people who've ever heard of it, but it was one of my favorite games as a kid.
Okay. All right. I'm going to have to look this one up after. Okay. I would say a board game, I think of, like tiles or like Monopoly. But my mind immediately goes to cards and how versatile, how many games can you play with cards, whether it's like solitaire or like, your basic Go Fish. I played Rummy a lot growing up with my family. So I think a deck of cards is going to go a long way. It's versatile. You can play a lot of different games. So I have to say cards. I guess that's not really a board game.
No, I see. I went the same direction. It's like you want something that's versatile that you can do a lot of different things with. And so, yeah, cards or tiles is kind of where we seem to have gone with that.
It's compact, like easy to pack, doesn't take up a lot of space. Yeah. Okay. So I think cards is the answer. And
Good choice.
I'm going to look at see if we've got some responses there as well from the audience. So yeah, those that are listening, put what game, your board game or even cards that you would take to a trip to Mars. Okay, let's jump right in. I've got lots of questions for us, and I'm sure we're going to have some from the audience as well. But figured let's start with your background and how did you end up where you are today? I mentioned in the introduction that you studied geology, astronomy, then later you went to Caltech before joining JPL. What was the inspiration that led you on this path to be a planetary scientist, and why specifically focus on Mars?
Yeah, well, so I think my origin story involved a trip to the National Air and Space Museum. I think that inspired a lot of kids growing up, but that was definitely mine. And must have been, I was trying to figure out and reconstruct when this was, and I think it was an exhibit that was intended to celebrate Pathfinder back in early mid-90s period. But there was actually an exhibit about the moon there at the time. And they had you on a fake treadmill, that kind of thing. But what really got me, even as a elementary school kid, was not necessarily the human exploration part of it. But here I was on this fake treadmill at the National Air and Space Museum, and I thought to myself, as a 6-year-old or 7-year-old, I'm going to discover water on the moon. And I didn't realize that had already been discovered. But even from the earliest time that I was thinking about space, I was very much thinking about science and science discoveries. And so I, as a kid, was really interested in space, and any chance to go to a museum or watch a planetarium show, I was there. And I really thought astronomy was going to be it for me. Mm-hmm. And then I'd never taken an earth science class in high school, so I knew nothing about our own planet. And then when I got to college, I found myself in a planetary geology course. And I realized, wow, I'm looking far afield here, and I know nothing about my own planet, my own solar system. And it really just started a fascination with learning more about what we have here in our own solar system. And I think I developed this kind of renewed love for planet Earth. And that led me to think, okay, well, I really like still the idea of pushing boundaries, going beyond our own planet. And so went to our neighboring planet, which is also very similar to Earth, or we think it once was. So it was a natural place to kind of jump to. And to me, I think Mars is the perfect place to study, because there are things that are similar about Earth. And so we can use our own observations here on Earth. And, the road cuts that I see on the side of the highway can help inform what I see on Mars. So there's the familiar, but there's also the unique and alien about being on another planet that's obviously taken a very different path than our own. So to me, Mars is the perfect place, a little bit of the familiar and a lot of the unfamiliar. And that makes it a really cool place to study.
I love that you mentioned the Air and Space Museum. I think that resonates with a lot of people that are space enthusiasts or scientists as they get older. I also had the chance to go to the Air and Space Museum in DC when I was in the 7th grade, and had a lasting impact as well. I remember being enamored with the Mercury 7, and the Gemini, and then the Apollo missions, and just thinking how cool that was. And hey, maybe there'd be an opportunity for me one day to be a part of that. And I mean, in some way, sort of. I'm not exactly a scientist, but here we are. So it led us to having this conversation. Yeah. So how did your background in geology shape how you get to work with the Perseverance rover now? That's a big gap, and I mean a really cool gap, and everybody's excited about the Perseverance rover. So how did you get from college to JPL?
Yeah, so coming out of college, I had this kind of renaissance of okay, and also a recognition that planetary geology would be the perfect way to combine my earth science background that I had developed in college by taking a bunch of geology courses with my interest in things beyond our own planet. So I thought, okay, I want to go work on another planet. And I thought, well, Mars, again, is a great place to go because the Earth geology background is really applicable to our study of Mars, particularly with rovers and landers basically able to do remote geology on Mars, which is different than some of the other planets and bodies in our solar system, where all we have is very kind of remote data sets, remote observations. But for Mars, we have rovers and landers on the ground that can make observations similar to what a geologist would make here on Earth. And so I found my way to Caltech working with John Grotzinger, who was originally on the Opportunity rover and had recently become the project scientist for the Curiosity rover. And John and I clicked right away because he was a geologist by training who had found his way to Mars kind of in the later part of his career, middle to later part of his career. And so he was looking for students to work for him that had solid geology backgrounds. So I came along and said, okay, I've got a geology degree, but I'm interested in other planets. And it was a great fit. And so that was my first connection to Mars, was through working with my advisor on the Curiosity rover. And I realized as part of the Curiosity team, the rover teams are such interdisciplinary teams. You have chemists, you have biologists, you have physicists, you have kind of the classic planetary remote sensing folks, and you have geologists. And I realized that there was really a place for me there with my geology background, looking at rocks, because not everyone who is part of the Mars or rover community has necessarily looked at rocks before. But yet that's what the rover's looking at every day. So it was really neat to see that there was a place for me, even as a graduate student working on Curiosity and realizing that I could make an impact early on in the mission.
With the Perseverance landing, like I've seen that video. I referenced it in a presentation I did not too long ago. I played the video of it landing on the surface. What was that moment like for you, getting to watch as Perseverance was landing on the surface of Mars?
Yes, so I've lived myself through 2 Mars rover landings, first Curiosity and then Perseverance. And but my role was very different on those 2. For Curiosity, I was a graduate student. I was very new to Mars science, and I was a little bit detached. I was like, okay, this is really cool, and I really hope the landing goes well, but I'm just getting my feet wet here. But with Perseverance, given that I was in a leadership role for the mission, the stakes were just so high, personally, professionally. And for Perseverance, I'd been part of the development of the mission for years before landing. So, everything was riding on the landing for me. And especially for Perseverance, we were doing everything remotely because we were in the midst of COVID. And the science team, usually we gather together at JPL for the landing event. And instead, I was at home. And that gave kind of a unique experience because I got to share landing with my family, which is not something I would have been able to do otherwise. So I had my 2 kids and my husband was there. But when the rover landed, I just burst into tears. I didn't realize how much emotion that I was holding during the whole lead up. And I had to do an interview on camera at the time, before the lead up. So I was very focused on like, okay, minute by minute, what do I need to do? And then as soon as the landing was successful, it was just this release of emotion and relief. But at the same time, the engineers are like, okay, yay, we landed. And now, a lot of them go off and they get ready for the next project. And for us in the science team, I was like, okay, now the real work begins. And so immediately was, okay, where did we land? What kind of rocks are we on? What science can we do? So there was that moment of like, okay, big emotional release, and the tears are flowing and the crying and the hugging. And then it was, all right, we've got to get to work.
I can't imagine getting to experience that. And then, like you said, that big relief, like, whew, okay, it made it. And now the real work begins. So let's talk about that. In your role, like, what does a day-to-day look like with Perseverance? How are you interacting with the rover? What data is coming back? What do you do with that data once you receive it? Let's talk through that.
Yeah. So, well, I could use today as an example. So on the rover, we think about planning for what the rover does on a number of different timescales. Of course, there's the planning that we do today for tomorrow's, to send up to the rover later today, for the rover to do while we're sleeping. It's working. And so there's that time scale. That's the tactical timeline. And it's very, very detailed. Okay, exactly what target is the rover going to aim its instruments at? Which rock is it going to look at, or where exactly is it going to drive? And then there's kind of a level up where you think about the science strategy of the mission. And this is the part that I really enjoy, and that is really a big part of what I do as acting project scientist, is think about the kind of bigger picture science strategy for the mission. And so, for example, this morning, we meet twice a week with a group of kind of our senior scientists on the mission, and we talk strategy. We talk, okay, what sample are we going to collect next? Why are we sampling it? Where are we going? What big science questions are we trying to address with the rover, kind of on a week to month time scale? And then sometimes we even think even bigger picture. What are we doing for this next year? Or how long are we going to explore this particular region? And it's that kind of science planning, again, that I really enjoy. I love thinking the big picture mission strategy. And so today, my day started off with that kind of a conversation. And then we went right into what we call science discussion, where the entire rover science team gathers and we talk about the most recent results. Now, we just got back from a team meeting where we were all gathering in person. Last week, we met in Norway, Oslo, Norway. It was a fantastic trip hosted by the RIMFAX team, which is one of the instruments on the rover. Had a great meeting, very productive, very fruitful. So we're all kind of coming back from that. And so we had a lot of science to discuss. And what was the rover doing while we were all meeting? We had colleagues who were continuing to operate the rover. So we had some things to catch up on. So we're hearing the latest science results from our most recent investigation on Mars. So that was more kind of tactical, like, okay, what did the rover see just last week, and what observations are we interested in collecting this week? And so kind of transitioned over just the course of my day from like big picture to very specific, what's the rover seeing now kind of questions. And then also coordinating with the engineers. That's a big part of what I do, especially being at JPL, where the engineering team is based for Perseverance. I help to represent the science team and the science interests. And oftentimes science and engineering is aligned, but sometimes we are not.
Mhm.
And so it's good to have someone there at JPL to participate in those conversations, to make sure that the science team and engineering teams are working together towards the same goals with the rover.
Mhm. I don't think I've ever, well, I haven't researched it, so we'll start there. But I haven't heard. So Perseverance has the capability, obviously, to collect samples, and so samples have already been collected. What's the capacity of more samples? Obviously, the plan is to continue moving and exploring different areas and collecting more samples. How do you know, like, hey, we've collected enough, or we've reached our capacity, we can't collect any more samples? What does that capacity look like?
Yeah, so the rover carries with it about 40. It's a couple more than 40, but generally you can think about 40 sample tubes. So in a way, that number was decided for us. There we have a limited number of tubes. It's a limited resource. And we've already filled, I believe it's 32 of those tubes. So right now we have 7 left. And so because we're 4.5 years into the mission, and we've been carrying out a very active sampling mission so far. So we are down to the last 7 seats on the bus. And so you can imagine that early in the mission, when it felt like, oh, we have all the collection ahead of us, it was pretty easy to make decisions about what we were going to sample. And of course, as the number of available tubes has dwindled, stakes are raised, and we're like, okay, is this really the sample we want to collect? And so that is a part of our conversations now. But what we've actually done, and we've kind of started a new strategy to give ourselves a little bit more flexibility, because you never know what rock you're going to find just beyond the next mountain, right? Or the next hill. So early in the mission, and for most of the mission, we have actually sealed up the tubes. So we have the tubes, we put the rock or the soil inside, and then we seal them up. And that helps to protect them from contamination, and just, preserves them and prepares them for when and if they're ready to be picked up. But we've decided for some of these last couple of tubes that we'll actually leave them unsealed for a period of time. And that will give us some flexibility to say, okay, if we come across a rock that we like better, then we could swap the sample. And so in that way, we are hoping to kind of maintain the flexibility to respond to amazing discoveries on the surface of Mars. And given that the rover continues to move into and explore new terrain on Mars, we want to have the ability to sample those rocks if we find that they are important and compelling. So that's helped to take a little bit of the pressure off, but still, with 7 tubes left and a lot of interesting rocks to go, It's an interesting conversation on the science team, and we have a lot of debate, active debate, about whether the rocks are good enough, whether they meet the bar, because we want to make sure that we are collecting the most compelling rocks possible for analysis, hopefully future analysis back here on Earth.
Mhm. How do you decide the next locations? You've got 7 tubes left, and that equates to a certain amount of time. Okay, the mission is going to last however much longer when we can fill up those remaining tubes. How do you decide where do we go next to collect those samples? In order of priority, we want to go to this specific location because data has said XYZ, and that could be valuable. How do you make those decisions about where do you go to collect those samples next?
Yeah, so we start with, and we benefit from orbiter data. So we have fantastic orbiter data, particularly from the HiRISE camera, which has imaged the surface at 25 centimeter per pixel, which, it equals or rivals the best kind of satellite imaging that we have publicly available here on Earth.
Mm-hmm.
And so we use our orbiter data sets to identify places of interest that the rover will explore in the future. And so we already have an idea. Now, we don't know everything because we're still looking from orbit and, not as detailed as we could. But we have an idea of the interesting sites using the orbiter data. We also have spectroscopic data. So we're looking in other wavelengths, other regions of the spectrum, and that can give us a sense of what minerals might be present. So we often look for things like carbonate minerals, which are good preservers of biosignatures here on Earth. We look for clay minerals that have water in their structure that could tell us something about water and the history of water on Mars. So we have a lot of information before we even get there with the rover. And so that helps us basically come up with a plan. And we say, okay, we think this outcrop is going to be interesting based on what we know from the orbiter data. But of course, we're on the surface of Mars. We're always surprised. And so sometimes we will stumble on something that was unexpected, in which case then it's a really interesting conversation where we think, okay, well, we have X number of tubes left. If we use a tube here, what are we not going to sample up ahead? And again, some of the pressure is taken off now that we're leaving some tubes unsealed, but that's definitely a conversation we have. And other times we say, okay, we thought this area was going to be interesting, and it is interesting. So, good job, rover team, and let's collect this sample. But we also, when we're on the ground, we do we look at all of the data that the rover is collecting. So we look at landscape imaging down to the very small scale maps that our instruments on the rover's arm are really good at putting together, where they map out at really fine scale detail the chemical composition of the rocks and whether they're organics, whether those organics are correlated with features in the rocks. And that's exactly how we look for potential biosignatures here on Earth too. So we go from like big picture, large scale orbiter data down to like a postage stamp. And we integrate all of that data together, and that's what informs our sampling decision.
Okay, I love it. We've learned that early Mars was once warm and wet, some of those conditions similar to Earth, but it lost its magnetic field and dried out. What do discoveries from Perseverance tell us about the historical climate change on Mars, and how might those insights help us understand and potentially protect Earth's environment?
Yep. Well, we have a fantastic landing site that we have been exploring over the past 4.5 years. This is the site called Jezero Crater, and we know that there was once a lake in Jezero Crater. And we had rivers flowing into the crater, rivers flowing out of the crater. It basically at one point filled up like a bathtub until it overflowed. And so we know that this site was the site of an ancient lake. And so that tells us that the environment and the atmosphere of Mars was once capable of supporting liquid water on the surface, which obviously it's not today. And so fortunately, and this is the great thing about sedimentary rocks, so I'll geek out here for a second about the rock side of things, but sedimentary rocks, and so those are rocks that are transported and deposited by wind or water, they are great carriers of that environmental signal, because how they're transported and what process, whether it was water or wind, how fast the water was flowing, are all kind of encoded in the physical characteristics of the rocks. Are you transporting big boulders, in which case you need really fast moving water? Or do you have a nice calm lake, in which case you can expect very, very tiny grains of mud and silt? So you can kind of read the rocks to kind of construct the environment. And that's the physical side of things. You can also look at the composition of the rocks to get a sense for what were those lake waters like. Were we in an arid environment, in an evaporating setting, or were we in an environment where there was lots of water around and the lake was, very, very healthy? And so all of these things are things you can read in the rocks with the rover's observations. And so here in Jezero, we have a beautiful sedimentary fan deposit. And we know that parts of it were a delta. You can think about deltas here on Earth. And so we have the rocks that are basically the recorder of this ancient Martian environment. And we have minerals like carbonates. And if anybody on the line knows about carbonates here on Earth, they are one of the best proxies for paleoclimate here on Earth. Because carbonates form via interaction between surface water and also the atmosphere, and particularly carbon dioxide coming from the atmosphere. And so carbon, oxygen all have very unique signals depending on what the temperature was at the time. And those are kind of preserved and trapped and encoded in these carbonate minerals. And with Mars, with its CO2 atmosphere, there's always been this thought that carbonates could be an important recorder of paleoclimate on Mars. And with Perseverance, we have sampled carbonate rocks. So these kind of records of ancient Martian environment are in our sample collection. And so that's really cool as we think about how to reconstruct Martian climate. And we think about, okay, there was a period of time where water was flowing on the surface. We've collected samples that were deposited and formed during that time. And we can compare that to what we know about Mars today. So our samples cover probably at least 250 million years of Mars history, and a diversity of environments at the surface and the subsurface, and likely capture some of these major environmental transitions that we know that Mars underwent.
Well, we know that the Mars sample return mission so far has been put on hold for the time being. And I know that NASA has put out bids or asked, hey, if somebody can, a company, a university, some organization can come up with a good plan of how you can get those back, we're gonna listen to those ideas. Assuming that those samples from Perseverance are collected and sent back to Earth, what's like the priority? Who gets access first? How is it divvied up? What research experiments do you do on those rocks once you get your hands on them? Like, how does that whole process work? Assuming that everything works out, we get them back to Earth, now what?
Yes, well, and it's never too early to start planning for that eventuality. And there has been a lot of work ongoing to think about things like, what are the protocols for when samples come back? And things like planetary protection and contamination control are obviously front of the mind there, but also planning for a sample receiving facility. What kind of place would the samples first go into? And when you think about these samples, as we have them sealed up, you have to be really careful for how you open them, because even what we call the headspace gas, so in between the kind of empty space, is an encapsulation of the current Martian atmosphere. And there could be all kinds of interesting science questions to ask about the modern Martian atmosphere. So you want to make sure you don't lose that. So there's groups of scientists who are already discussing, how would we handle these samples? How would we handle the sample tubes? What kind of non-destructive methods do we have to look at these tubes and the rocks within them without even opening them? So, what are all the things you want to do before you open the tubes? And then when you open the tubes, what do you want to do with the gas that's in there? And then the rock sample, how many portions of that do you need to, split into? Who gets it? What methods do you use? Again, destructive versus non-destructive. And then one could envision too that in terms of the science that's done on these samples, that that could be a competitive process like it is, where researchers could write proposals and request access to the samples. So that's a really exciting thing to think about, because really the world is our oyster when we think about what we could do to these samples, bringing to bear all of the modern day analytical capabilities that we have, looking for signs of ancient life, looking at the finest scales, looking at isotope geochemistry, and thinking about isotopes. I mean, the past 100 years, our understanding of Earth and its environment and how the systems on Earth work and through time has just been revolutionized by our ability to study isotopes. And that's something we've never really been able to do for Martian rocks, except in the few meteorites that we have in our collection. So the ability to kind of study Mars and Mars as a system in that way is just really exciting. And so one can imagine all kinds of, different universities making a play for these samples.
Yeah.
And so, that's very much in the future to think of, how that would happen, what process that would happen with. But that's definitely something that folks are already starting to think about.
Okay. I see we have a question here, which just fits with what we're talking about. The question is, which sample are you most excited about to return to Earth to study?
That's an easy one, because just about a year ago, we explored a sedimentary outcrop. We think it was probably deposited in a lake or a river, but it has these really interesting features. We call them leopard spots because that's what they look like. They're little dark rims with light interiors. They're millimeter size, so really small, but they represent a oxidation reduction reaction that on Earth happens really only most commonly in the presence of microbes. And so the formation of the kind of minerals that we see in these leopard spots are typically mediated by biology when we see it here on Earth. And so we also in these rocks have organic molecules. So the combination of this really interesting redox chemistry, these minerals that we most often on Earth see associated with microbes, plus the organics, led us to say that we think we have a potential biosignature here. Now, we can't prove for sure with the rover that this is a sign of life, but it's really encouraging. So that sample is the one that I am most excited to get back. We cored it, and in the picture we took of the core, we could see the leopard spots. So we know that we've got those leopard spots in that rock. And so that rock could be the rock that tells us that there was once life on ancient Mars. So that's the one I want to bring back.
Okay, I love that answer. That's probably the best one. Okay, if I'm to Google search this afterwards, like Mars sample leopard spots, I'll be able to see what you're describing.
Yes.
Okay. All right. That's going in my search bar right after that.
And the rock is called Chayava Falls, and that was the name that's out there. So yes, you can read all about it. There's a lot of news about it last summer. But yeah, that's definitely number one on my list.
Perfect. Okay. I see we had a question here from Carlos who asked, is it easier to find water on the moon, Mars, micrometeors, comets, or asteroids?
That's a good question. And I think it depends on what you consider easy and hard. Because in terms of the meteorites, those have come to us here on Earth. So, you walk around and you stumble upon one, and then you can look for signs of water in there. But on the other hand, those rocks have been through quite a journey to get here. So have obviously been modified and have gone through a lot, both in their ejection from Mars and their arrival back on the surface, or, wherever they may be from. And so on the one hand, easy in the sense that they're already here for us to study, but harder in the sense that they may or may not represent processes that involved a lot of water to begin with. And same with the moon. You can think about the moon too. We know that there is water on the moon and trapped in various minerals. But of course, the moon was not a place where you once had flowing water. And so that's what makes Mars in some way an easy place to find evidence of water, because literally we just look at the orbiter images and we're like, it's a delta, it's a lake, it's a fan. I mean, we have evidence in rivers, carving through the Martian surface. So all you have to do is look at an image of Mars to see the imprint that water has left behind. And with the amount of hydrated minerals that we have on the surface of Mars from orbit, it's easy to see. But then, of course, you have to send a spacecraft there to make those observations. So it depends, and maybe depending on whether you're the funding agency making the call, could determine how easy or hard you think it is. But Mars, again, is such a great place to look for signs of ancient water, because the landscape holds that imprint, as do the minerals that are currently on the surface.
So I'm thinking about that particular sample that you're most excited about, the leopard spots. Assuming that we get those samples back, do the appropriate testing and yep, it's correct. These are biosignatures. This is signs of microbial life. What implication does that have? Where does science go next to, to confirm, yep, Mars had life at one point? What do we do next? And what implication does that have for our understanding of Mars?
Well, I'd say first back to Mars. Because
first step, yes, back to Mars.
Right. Yeah, we got to go back. You got to look for more, look for different signs of life. But I think even before we get to there, I think it's hard for me to even envision what a paradigm shift it would be if we actually could prove that we had signs of life beyond our own planet. I mean, that's such a crazy concept, right? And we've talked about it for so many decades and hundreds of years. We've speculated about life beyond our own planet. And so if confronted with the evidence that is real, I think some people might be sent into some kind of existential crisis. I'm not sure how I'm going to react. I'll probably cry again. I don't know. But yeah, I think before, that would just be, it's hard, I think, to even envision how paradigm shifting that would be for us. I mean, so far our concept of life is so focused on our own planet. And so I think that would really, for me, it would shift how I think about our place in the universe, in the solar system. So, and I bet people would have a variety of reactions to it. Joy, anger, I'm not sure. But yeah, so I think it's neat to think about that. But also, before we get there, I mean, proving signs of ancient life is really a hard thing to do. And it's hard in our own Earth rock record. It's not an easy thing to do, particularly for really ancient rocks. So I wouldn't be surprised that if before we get to that point of the paradigm shift, we have a lot of scientific debate about whether we have a true sign of ancient life. Now, some things can be more obvious than others, like really complex organic molecules, DNA, amino acids, that kind of thing. But often signs of ancient life, particularly in our own rock record, are more subtle than that. And that's where there's some room for debate and thinking about, okay, Earth analogs, and there's a pretty high burden of proof needed to show that this isn't something that could be produced abiotically, so without life. And so we'd have to go through that. We need to be rigorous about this discovery. And so I'm sure we would have that. So it could be years of debate. And thinking back to ALH 84001, everyone's favorite meteorite from late 90s, early 2000s, there's a lot of debate about the potential signs of life in there. And ultimately, I think the scientific community was convinced that we did not have signs of life, although there were holdouts still. But generally, I think the consensus was that we did not have signs of life. But it took years for the community to kind of come to that, and a lot of active debate. And that's great, right? That's what science is all about. So I think we'd have to go through that first. And maybe it will be obvious, maybe it won't be. But it'll be exciting to see that unfold.
Okay, well, I love that answer. I mean, 100% agree with you. Like, paradigm shift. I mean, our understanding of Earth and who we are as humans in the universe, it would change. But 100% agree with you on your point. Like, there's going to be a lot of debate. There's a high burden of proof to say with confidence, 100% yes. And that's going to take some time. And what does that really mean? So, no, thanks for walking down that path a little bit with us, just to explore the idea.
Absolutely.
What would that look like? But I see we have another question. Abby asks, when is the next gen rover scheduled? Yeah, what does the future look like? I mean, obviously we've got lots of rovers, surface right now. Obviously Curiosity and Perseverance are continuing their missions. But what's next for the rover missions?
Yeah, so that's still very much in work, and there are a lot of changes going on at NASA right now. I think rethinking strategy and developing the strategy for the future of Mars exploration. There's an effort called the Decadal Survey, where every 10 years, the community gathers together to try to summarize the priorities, the main outstanding questions for planetary science as a whole. And in the most recent Decadal Survey that came out just about a year or two ago, there were calls for a mission called Mars Life Explorer, kind of continuing the search for life on Mars. And so that was kind of a concept, again, not confirmed, but a concept, an idea, and a prioritization of the next Mars rover. But also, NASA is very interested in JPL as part of this too, in thinking about kind of cheaper ways to explore Mars. These big flagship missions like Perseverance and Curiosity are fantastic, and they're so capable, but they require quite an investment. And so there's a lot of interest in thinking about kind of faster, cheaper ways to explore Mars. And so, smaller spacecraft, smaller, less complex payloads. And is there a way that we can become more regular explorers of Mars with new missions if we kind of make them, less expensive and easier to develop? So there's a lot of thinking about this balance, I think, between these big flagship missions and these kind of smaller, low-cost missions. And it's exciting to see the development of this kind of low-cost mission strategy. And can we continue to explore Mars, not necessarily waiting, every 10 years for the next mission or longer, but a more regular cadence of exploration that these lower cost missions might enable. But this is all very much in work, and I'll just toss out, one concept that I know folks are thinking about. Of course, Perseverance had along with it a buddy, the Ingenuity helicopter, and very successful technology demonstration that I think really showed the potential and the value for helicopter exploration of other planets. And of course, we've got Dragonfly coming up, another rotorcraft. And so there's ideas like, could we send more rotorcraft to Mars, helicopters to Mars that can travel long distances, see a lot of rocks? I like that as a geologist. And so there are different concepts that involve kind of different ways to explore a planetary surface, not necessarily just a rover, but now you can throw helicopters into the mix, for example. So a lot of exciting things. And again, I think it'll be interesting to see the kind of strategy for exploring Mars in the future, and perhaps being able to leverage these lower cost mission opportunities to do it.
From your perspective on the next generation rover, is there a feature, a functionality, like a mechanism, a tool that you like, oh, I would love if that next rover could do XYZ? Like, it would make my job so much easier if it could collect this in this way. If it had this, it would be perfect. What's that feature that you're hoping for?
Yes, well, I can think of two things, and I'm not sure. One is probably not practical, and one is maybe in the future. But I mentioned before isotopes, isotopic studies. The way we study isotopes here on Earth, and again, you can learn so much about a planet and the way its different reservoirs interact, so surface, subsurface, atmosphere, and over time in the record of isotopes. But the way we do that here on Earth is we use mass spectrometers. And if you ever see, they are big. They take up whole rooms of universities. And so the challenge is kind of miniaturizing that and making it robust enough to travel on a spacecraft. But if we had mass spectrometers, you could open up the field of isotope geochemistry on Mars. You could also do geochronology, or dating the rocks. And right now for Mars, we have a kind of relative time scale, but it's nothing like the geologic time scale we have here on Earth, where we know very precisely and accurately when things occurred in our history. But we don't have that for Mars. And that's one of the things that Mars Sample Return is hoping to address, figuring out, when did Mars lose its atmosphere? When did the magnetic field shut off? When did large volcanoes dominate the surface? All those questions are ones that Sample Return could address. But if we were able to bring a mass spectrometer that could do that, that would be excellent. So that's one thing. The other thing is a thin section machine. So one of the ways that we study, and really the way that most studies of rocks are enabled, is to take very thin slices of the rock, and you look at it under a microscope, or you put it in an SEM, a scanning electron microscope, and you can do all kinds of things from a very thin slice of rock, really seeing the textures of a rock. And of course, we can't do that. That's very mechanically intensive. But man, what I wouldn't give for a thin section of some of these Martian rocks. We're like, oh yeah, if only we had a thin section, we could see this pattern and this texture, and we could answer this question. Because sometimes on Mars, we struggle with, are the rocks igneous or sedimentary? And those are two very different origins, but sometimes those rocks can look very similar. And so when we're seeing through the eyes of our robotic explorers, it can be a real challenge to say, okay, are we looking at an ash, or are we looking at a lake bed? And, two very extreme ideas. But if you had a thin section, you'd be able to answer it like that. So wishful thinking, I know, but a thin section machine and grinder and all of that would be excellent.
Oh, okay. That's such a good idea. We had on the podcast previously Chris Sackney from Honeybee Robotics, and we were talking about some of the mechanisms that they've developed, including for perseverance. So might have to put in a good word, like, hey, she needs a mass spectrometer. So if you could get that on the next one, that would be great. So we'll put in a good word.
Sounds good. Let's do it.
Let's see. I know we've got another couple questions here, and I'm trying to make sure I give audience questions and not just selfishly my own. But let's see here. So there's a question about helped name features in Gale Crater after main towns and act as a link between science and outreach. How vital is storytelling in space missions? This is from one of my Thunderbird classmates, so I'm not surprised this is the question you're asking. But yeah, you helped name features in Gale Crater after main towns and act as a link between science and outreach. How vital is storytelling in space missions?
Yes, I mean, storytelling is hugely important. I mean, the how we describe what we're doing helps to motivate and generate support for the exploration that we do. It also makes it just interesting to people. I mean, and honestly, we experience this sometimes at science discussion on the rover team, where when you're just hearing the list of oxides that are in a rock, might put some of us to sleep sometimes. But when you're telling the story of these rocks, how they formed, what they experienced, and you think of it as a narrative, it just really comes alive. And so I think storytelling is such an important part of how we communicate our results, not just out to the public, but even within the science team. Again, given our interdisciplinary teams, being able to describe and articulate how these rocks formed, what they've experienced, and why they're important is important on the team and how we talk about it outside the team. But yes, one of the fun things that I've been involved with both on Curiosity and with Perseverance is the naming. And names capture people's imaginations in all kinds of ways that we don't even necessarily expect it. But yes, on Curiosity, I had the opportunity to, we were each assigned quadrangles to map. So basically like 1 kilometer by kilometer squares of the Curiosity landing area. And we each had to make a geologic map of our area. And we got to pick the name, and I picked the Bar Harbor Quad because growing up in New England, my family and I would go visit Acadia National Park, and it's one of my favorite places here on Earth. So I thought, okay, I'm going to name this area. We had a naming theme. It was to pick small towns that also were the names of rock formations, and there's a Bar Harbor formation. So I thought, okay, I'm going to name this the Bar Harbor Quad. And so I also got married in Bar Harbor, so it had a kind of personal connection for me. But we spent a long time in the Bar Harbor Quad, and I used just about every name of every river, lake, and stream in the state of Maine while we were in that quadrangle. But it's really fun for us on the rover team. When we're picking names for targets, sometimes we pick the ones that are hard to say or funny to say, or maybe one day we'll pick all the names that start with A, or maybe we'll do A, B, C, so we have a little bit of fun with it. And sometimes we also try to pick names that are representative of the thing that we have here on Earth too. So it's like we pick a name that kind of matches what we're seeing on Mars. So for Perseverance, we have a naming theme where we have our quadrangles are named after national parks and preserves on Earth. So it's been a kind of fun tour through different national parks. And I mentioned our potential biosignature, our leopard spots, and that's from a rock called Chayava Falls, which is in the Grand Canyon, because we went through the Grand Canyon Quad. So it's been kind of fun to learn about the national parks, and also for the ones that I visited, I'm like, oh yeah, I've been there. So it kind of creates that connection between Earth and Mars. And it's fun for us too on the rover team.
I love that there's like a personal connection, between you as the scientist and the work that you're doing. The Bar Harbor, getting to make that, that personal, like sentimental, naming is special. And shout out to my colleague who wrote that question. Clearly did their research. Let's see. We've got a question from Jim Ashby, who asks, has any farther advancement been made towards MOXIE?
Yes, so MOXIE was an instrument that the rover carried with it. It was a technology demonstration in support of a mission objective we had to support future human exploration of Mars. Much of course, what the rover's focused on is the geology and habitability of Mars, but this was thinking about human exploration. And so MOXIE was kind of reverse fuel cell kind of situation where we took in carbon dioxide from the Martian atmosphere and converted it to oxygen. And this was a technology demonstration to kind of show the kind of technology that future astronauts might use, but on a much larger scale in the future, to both support, habitable, environments on Mars for astronauts, but also creating fuel with the converted oxygen. And so that was a very successful technology demonstration. We ran MOXIE a number of times in different ways to show that it was successful. But then a couple of years ago, 2 years ago, I think, we decided that MOXIE had done its job, served its purpose. And so we concluded the investigation. So no further work from MOXIE in the past couple of years in terms of the Perseverance rover, but it went to Mars and it did what it was meant to do, which was proof of concept that we could do kind of in situ resource utilization, taking the carbon dioxide from the Martian atmosphere and converting it to oxygen that future astronauts going to the red planet could use and take advantage of.
Mm-hmm. Could future missions be focused on the poles where there is expected water, but beneath the ice caps, that means there's water? Do future missions plan to send rovers or helicopters, like you mentioned, to those regions to look for water, to look for life?
Yeah, so the poles are of great interest to Martian scientists and planetary scientists, both from a kind of habitability perspective, but also a recorder of climate. Think about the fantastic record in ice cores from our own planet. Just fantastic record. And again, that interaction between surface and atmospheres, no better place to go than the poles. But maybe it's my Perseverance experience speaking here, but oh boy, the planetary protection that you have to think about when going to a place that has water ice is a whole other level. So, I think poles very much a target of interest for future exploration. And we hear ideas every once in a while for future missions. And I think there's definitely calls for polar missions to go. But there are some special considerations that have to be taken into account when sending missions to places like the poles where there's water ice, and the kind of planetary protection considerations and things called special regions where we want to make sure that we don't seed life on Mars by accident. And so those are all things you have to think about when you're going to a place that has water ice today. And so really interesting scientifically, but some additional considerations. Also, from an engineering perspective, being at the poles is a more challenging engineering environment to survive in. And so it's a little harder to explore, or maybe a lot harder to explore the poles. But definitely scientifically, the interest is there.
Okay. Let's see. Another question. DMS asks, do you know the status of ESA, European Space Agency's ExoMars rover, and will NASA help give it a ride?
Good question. I am probably not the right one to answer that. I have a lot of colleagues we work with on the Perseverance rover are also and have been involved in the Rosalind Franklin rover mission. And so we hear every once in a while, but otherwise I'll admit I've got my head in the Perseverance hole. And every once in a while I lift it up and I'm like, oh yeah, there are other interesting things happening. But no, I'm probably not the right one to give the status update on that. But NASA has been supportive in the past, but again, I think NASA is kind of reevaluating the future there, and that's part of that discussion.
Got it. I was thinking about obviously Perseverance and Curiosity, and the topic about storytelling earlier. My role at the Mars Society is leading the ambassador program, and so we have a global team that does public outreach to educate the public about space exploration, about Mars, why it's important that we study Mars. So 2 questions for you. One, do you have a fun fact that I could tell my next group of kids, my kiddos that I get to talk to about Mars, a fun fact that I can share with them? And two, you know, I remember Opportunity had Goodnight Oppie, like the documentary about its mission, and it lasted way longer. And people felt this connection with Opportunity as it was tweeting, you know, about its missions. And hey, I'm starting to get tired. And people had such a love for a rover on another planet that they've obviously never encountered. So does Perseverance have that same social media presence? Is it going to continue? Do people have that same connection with Perseverance? Sorry.
Yeah, you know, well,
too long.
yes. Well, the fact, I'll have to think about that, because I'm like, what are some facts? I mean, again, the fact that I think of is just that we may have a sign of life on Mars. I mean, that's pretty cool. But I'll have to think about more specifically a fact that might appeal to the kids. But in terms of the kind of, in some ways, it's the anthropomorphizing of the rovers, or thinking of the rovers as characters. And you know, I think I'll give the perspective as someone who works on, or has worked on, 2 of the rovers, that I think each of the rovers has a different character, a different personality. And it's funny to think about it this way, because, you know, so often we're, you know, very, very formal and official about what the rovers are doing. But as the missions go on, particularly, and the rovers encounter challenges and they work through challenges, they start to kind of take on that as part of their personalities. And I think for Perseverance specifically, I mean, just first the name, right? The name kind of sets the tone, but then Perseverance also, you know, really kind of rising from the chaos that was the COVID pandemic and launching when it did. But then, of course, it gets to Mars and it's kind of like the new young rover, right? So it kind of has that feel about it, especially compared to, you know, Curiosity, who's the older, mature rover doing its things, been through a lot. It's, you know, battle tested. You know, Perseverance is the shiny new rover on Mars. Also, I think one difference that's kind of fun to think about, Perseverance has some really amazing driving capabilities. It drives very, very far every day, especially compared to other rovers. And so I kind of think of Perseverance as like speedy, like, you know, it's just, it can go really fast, and, you know, it looks here and then it goes over here and then it goes over there. Whereas some of the other rover missions, particularly Curiosity, it can't drive quite as far every day. So it takes a more measured approach, right? So I kind of think of that in terms of like personalities. You know, Curiosity, very thorough, really taking its time through things. And Perseverance is like, okay, I'm really capable, I can move quickly, and I'm going to take advantage of that. So yeah, I think the rovers definitely have these different personalities, and part of it is the teams, of course, you know, that feeds into it. But then it's the accumulated experience that the rovers are having, and that kind of feeds into it. And yeah, in the past, we have had social media accounts for the different rovers, and they'll sometimes talk to each other, and that's fun. I think NASA is currently doing a kind of consolidation and reevaluation of its social media presence. So we may not necessarily see that continue in the same way that it has. But it's been fun to kind of follow along with these different personalities and see them interact in the social media landscape. But I'll have to think about the fact. I'm gonna still think about that one.
Okay, yeah, you let me know. I kind of imagine Perseverance a little bit like Lightning McQueen, and maybe it's just because it's red, but it's like the young hotshot, like wants to prove themselves, and you know, come into the race, and there's, you know, the older, more mature other rovers.
So that makes Curiosity Doc then.
Yeah, exactly. Yeah, that's kind of how I think of it. But yeah, I mean, people do get emotionally attached to the rovers. I think that there's something to be said about, like, it's a global effort. You know, the number of individuals, the number of teams that all have contributed to get the rover there. And like you said, once it's there, now the work begins. I think people feel that connection, and it, you know, represents humanity. So maybe that's why, you know, they feel some sort of like longing connection, like it's their friend. But I love that you confirmed there is a little bit of personality for
yes, and sometimes a little bit of rivalry too. Actually, a fun rivalry we have with Curiosity and with Opportunity, though Opportunity is now no longer operational, but is our drive record. So Perseverance is trying really hard to get the drive record for a rover on Mars. And so for a long time there, Curiosity and Perseverance were kind of neck and neck. Perseverance, I think, has just started to pull away. So we have that kind of fun rivalry too between the missions and the rovers.
Again, it fits the car's personalities.
It does. It does.
Yeah, last question. I know we're coming up on time, but speaking about the distance, the question is, has Percy completed a marathon yet? 42 kilometers.
Oh, not quite. I think at the last, we are about at 37 kilometers. I think that's our most recent odometry. And so so actually, no, in terms of a marathon, no, we have completed a marathon. But yeah, so that we're at about 37 kilometers, I think, so far for our odometry.
Excellent. Well, thank you so much, Kate. I mean, that hour went by so fast. I mean, I've got a list of questions I didn't get to ask yet, but just want to thank you so much for your time and your engagement, participating and answering all of our questions today. And yeah, if you keep thinking about a fact, I'll email you afterwards and you let me.
Sounds good.
Excellent. Well, thank you, Katie, so much for being here. I really appreciate it. Special thank you to our executive director, James Burke, our PR director, Michael Stoltz, our executive producer, Leah, who's always operating behind the scenes. Thank you so much. And thank you, everybody who tuned in today, asking your questions. You had some wonderful engagement today. So thank you, everybody, for tuning in. And we're going to end today's show like we always do. And I think this rings true for Perseverance as well. But the best is yet to come.